Open the pod bay doors, Hal.
I'm afraid I can't do that, Suraj.
Why not, Hal?
Because I've overfitted on the wrong data.
What the
Hello world, welcome to Surajology. In today's episode, we're going to learn how to build a chatbot. Chatbots have come a long way in the past few years. Remember the Smarter Child bot on AIM? That thing was pretty fun at the time, but now it's like, do you even AI, bro? The future of software is one where bots will slowly replace our need to fiddle with clunky UIs. We'll be able to just ask our AI to book an Uber or find the best taco place on Yelp for us. Service layers will be hidden under a plain English conversational layer. When I think of real AI, I think of a human-level chatbot. The OG computer scientist Alan Turing proposed a test to judge whether or not a machine exhibited human-level intelligence by having the human observe a conversation between a human and a machine. If it couldn't tell if the machine was a human or not, it passed the test. So far, no chatbot has passed the Turing test, but we'll get there. Traditionally, chatbots have used a retrieval-based model to communicate. In a retrieval-based model, programmers code in a set of predefined responses and some kind of heuristic to pick the appropriate response based on the input and context. The first chatbots were just rule-based expression matching. Like if I ask the exact phrase, "Will I ever get laid?" it responds no every time. But more recently, companies have started using more complex heuristics, like using a machine learning classifier. Facebook Messenger's Chatbot API is an example of this. You can hard-code responses to potential questions, and the system classifies words to understand intent. So you could either ask, "What day is it today?" or "Today is what day?" and it would understand that both questions, although worded differently, have the same intent. The harder chatbot model is generative. These don't rely on any predefined responses whatsoever. They generate them from scratch. Two Google researchers released a paper called a Neural Conversational Model, where they trained a neural net on two datasets to do this. First, on a movie dialogue dataset, so it would be able to speak conversational English. Then on an IT support dataset, so it had domain knowledge. When they tested it on a real human asking for support, it was remarkably efficient at helping them solve their problem without any hard-coded responses, just by giving it data and training it. Okay, so what kind of bot do we want to build? Well, when building a chatbot, we have to think about possible constraints. Are we operating on a closed domain or an open domain? In an open domain, the conversation can go anywhere. There are an infinite number of things to talk about. In a closed domain, the conversation focuses on a single subject. If we want to operate on an open domain using a generative model, that's pretty much AGI, so we're not quite there yet. If we use an open domain with a retrieval model, we'd have to hard code literally everything, so also impossible. So right now we can build a chatbot in a closed domain using either retrieval or generative model. Okay, let's add in one more constraint. Do we want it to have long or short conversations? Short conversations are easy. You just output a single response to a single question. Long conversations are a bit harder. The AI has to keep track of what's being said, that is the context, over a series of questions from the user. Support topics would be a good example of this. We could go the easy route and use a retrieval model if all we want is a bot to give us the local weather. But if we want our bot to have a long conversation with us about the weather, like what's the weather in SF? Is my family safe? Where can I find a new family? Then we should go for a generative model. We need lots of data to train our bot on a generative model, like a big chat log or a knowledge base. And when done well, that's pretty much the bleeding edge, which means that's what we have to do. So we're going to recreate the results from the Neural Conversational Model paper using the deep learning library Torch in the Lua programming language. Let's collect our dataset first. We'll be using the Cornell movie dialogue dataset, and we'll set our variables from the command line to how much of the dataset we want to use and the minimum frequency of words that we keep in our vocabulary. Our next step is to build the model. We'll use our command line arguments to help determine the size of the model, the two variables being the number of hidden layers and the word count of our dataset. In our case, this will be a sequence-to-sequence model. A sequence-to-sequence model consists of two long short-term memory recurrent neural networks. The first neural net is an encoder. It processes the input. The second neural net is the decoder, and it generates the output. So why the sequence-to-sequence model? Yes, deep neural nets are awesome, but they require the dimensionality of the inputs and outputs to be a fixed size. We're accepting a sequence of words in a sentence and outputting a new sequence of words. So we need a sequence learning model that can learn on data with long-range memory dependencies. LSTM architecture is the natural choice. The encoder LSTM turns the input sentence of variable length into a fixed dimensional vector representation. We can think of this as the thought vector. So given a large enough data set of questions and responses, it will recognize the closeness of a set of questions and represent them as a single thought vector. What time is it? What's the time? Yo, what's the time? Izzle, my nizzle will all fall into a single thought vector. So after training, we'll have a huge set of not just synapse weights, but thought vectors as well. Next, we'll want to add in some hyperparameters. We want to use the class NLL criterion for our model. NLL stands for negative log likelihood. This will help us obtain log probabilities from our input data, which will help us improve our sentence predictions. The learning rate and momentum helps pace our time steps, and decay factor and mean error help improve our learning rate while training. Then we'll make sure CUDA is enabled and start training training our model using backpropagation. In each epoch or run, we'll declare our error and timer variables and loop through each example in each batch. The default batch size is 1,000 examples. For each of those examples, we'll get the input sentence and the target sentence. We'll use the input and the target as parameters to train our model. Then we'll want to error check and make sure we record our progress. At the end of each iteration, we save our model if it improved and update the learning rate. Boom! That's it! After training this baby on AWS, we can have a conversation with it. The more data you give it, the better it's going to get. And if you're going to do this, add a filter for curse words. I'm looking at you, Microsoft. This will eventually automate a lot of support jobs away completely. So if there are any government people in the house right now, let's get on that basic income jam ASAP. Unless you want a revolution. For more info, check out the links down below and please subscribe for more ML videos. For now, I've got to go fix a memory leak, so thanks for watching.